Okay, so we're going to look at vectors, and the vectors have both magnitude and direction. When you add vectors, Jade took physics. Different ways you can add vectors. When you add vectors, you add them head to tail. And what they mean by head to tail is that when you draw a vector, it's going to be a certain length, which is going to determine the magnitude of it. So you would draw it to scale. So for an example, if it was a magnitude of 5 newtons, you might let 1 newton be equal to 1 centimeter. So you would draw it 5 centimeters long. And then the arrow is going to determine the direction of that. So how this would, like a application of it would be if you have a boat, or think about your the big radio towers or cell phone towers. They're going to have the big cables coming down off of it to support it. So you might have a cable going in this direction off of it. You have another cable going in this direction, and then you're going to have one going in this direction so that your tower is in equilibrium. And the angle at which they're going at it and the magnitude of them have to balance or equal 0 so that it's in equilibrium and not moving. If you were to add these together, I should change this, different colors. And these may not work out, but if you were to add these together, what you would want to do is you add them head to tail. So the tail is the end that has like an end point if we were looking at it as a ray, and the tip is going to be the arrow tip segment of your ray. So to add them head to tail, you can add them in any order, but you could take and add these head to tail would look something like this. Now, obviously, that one would not be in equilibrium because your ending point's not the same as your starting point. So what your object's going to do, or where your object is going to move, is going to be from the tip, the end, or the head to tail. So you could say the tail, or the end of the very first vector to the tip of the very last vector. And this right here is what is called your resultant. That's the result of what your object's going to do. You could talk about it if you have tugboats that are pulling in ships. Where is your boat actually going to go based off of the length of the cable that they have attached to the tugboats that's going to be pulling them into bay or whatever? I don't know, the cell phone towers or something. There's lots of things where you got to talk about when you put them into equilibrium, and each one's a specific vector. Maybe it's just pulling a boat into the dock out of the lake or something. We can add these vectors together. Now that's if you were adding them graphically, you could do that, which I don't know if you did that in physics at all. If you draw them to scale, you can add them graphically, but we're going to look at another way to add them. That's not necessarily going to be graphically. We can add them together by using sine, cosine, tangent, and making sure you add the x values together and the y values together. Because if I were to look at the resultant, we know that a vector, when you have a vector, we can break it into 2 components. Those 2 components that we can break it into, let me get a different color here. We can break it into the x component. Ooh, can you see that? Yes. I wanted to just make it a lighter blue. Maybe this would be better. So we can break it into an x component, and we can also break it into a y component, which is right here. So we have 2 different components you can break it into, because that's actually what your force is working with. When you talk about this angled vector force, part of it's going into moving it horizontally, and the other part's moving it vertically. If I talk about the red vector, that looks like I have it straight down. So if I break that into components, there's no horizontal component. And then if we look at the green vector, we can break that one into 2 separate components as well. One component is going to be the x component, and the other one will be the y or vertical component. Is that one going to work? That looks like about the same color, doesn't it? is definitely got to be a different color, but when you put it right on top of the other. So you break it into the two components, and what your object, the resultant is going to be, is when you add the x ones together. So what we're going to be doing is we're going to be taking these x components, and what happens when I add the x components together? It's going to end up going probably in this direction. The resultant is going to be this direction, the difference of the two, right? Because one's going to be a positive and the other one's going to be a negative. So we're going to end up this way a certain amount. And then you can take those vertical or the y components and we can add those together. And when you add those together, you're going to say, where am I going to end up? Which one looks longer? The up. If I draw it like that, you think it's up. So then my resultant is going to be up here somewhere. And then if I put those two components together, if I add these two components together, which if I talk about head to tail, then my overall resultant for where my object is going to go is going to be from the end of the first one to the tip of the second one, and there's where your object's going to go, which is depicted right there in that diagram. So they have broken it into the x and the y factors together. So in order to add vector quantities, you have to have them in XY format. You can't have them in a measure of like a magnitude with an angle of so many degrees. I think there is a key on your calculator that can allow us to get to that if we really wanted to. So for an example, if they tell you to find, I ask you to find the resultant. The resultant is just where it's going if I talk about head to tail, head to tail. So find the resultant. Now you have to be careful. Resultant is going to be where the object goes. A little bit later, they might ask you for equilibrium. The equilibrium, if I come back over here, the equilibrium is what puts it in equilibrium. So what puts this in equilibrium would be another force in the opposite direction with the same magnitude. Because if I pull in both directions with the same, opposite directions with the same force, are you going to move? No. So this is the equilibrium. Versus the resultant. That looks a little bit longer than the other one, doesn't it? Shorten it up. Equal in magnitude, opposite in direction. So just be careful of which one they're asking for, because I bet if I look on your problem set, on page 209, number 6 says find the resultant, but number 7 says find the equilibrium. To find the equilibrium, you'll have to find the resultant first, and then just 180 degrees opposite of that. Okay, so find the resultant of 4, a magnitude of 4 at an angle of 20 degrees. So I'm going to take that force and I'm going to add to it 7 at an angle measure of negative 230 degrees. First thing I like to do is just visualize where my forces are at. So first of all, I have this force of 4 at 20 degrees. It's going to be somewhere over here, right? Then I have a force of 7 at negative 230 degrees. Where's negative 230 degrees? The third quadrant. What's your reference angle? Here's your reference angle. What's that reference angle going to be? 50 degrees. So here's a 50-degree angle. This has a magnitude of 7. This has a magnitude of 4, and here's 20 degrees. Now, I will show you 2 different ways to work through this. Your book is only talking about one. The first one they are going to talk about does involve breaking it into, let's figure out what this magnitude is, and then let's figure out what the x component is for the other vector, and the end result is going to be the difference between those two, right? In the direction of the larger force. So I got to figure out what is the red, what is the green component. You've done that already. because you've gone from polar to rectangular and rectangular to polar. So we want to go from polar into rectangular format. So if I talk about 4 at an angle measure of 20 degrees, could you tell me what is that in rectangular format? Rectangular format, this is your I, right? And this is your J. So to find I, you're going to take the cosine of 20 degrees is equal to adjacent over hypotenuse. So you got to take 4 times the cosine of 20. Could you do that on your calculator for me, please? It's got it. I'll just do that. And if we look at J, how are we going to find J? The sine. Are you okay with me just saying it's going to be 4 times the sine of 20? Are we okay? Are we at that point? Or do I have to set it up in the equation? All right, 4 times the sine of 20. Now we notice that those are both what? Based off of the quadrant, I know that they are both going to be positive values. If I take the second one, and I want to find the X or the I and the J or the Y, put that into rectangular format for me. So to find the X value, it's going to be 7 times the cosine of 50 degrees. What's that give you? 4.5. What do I notice about that value? It's going to be negative. And then I need 7 times the cosine of 50. Sine. Man, I want to use 4 and cosine instead of sine. 7 times the sine of 50, which is going to be 5.36. And that value is going to be positive. So what we want to do is figure out where is that resultant at. Now, I don't have this drawn to scale. It's just a rough sketch. But if I were to look at my diagram, if I were to add them head to tail, it doesn't matter which one you move. I'm just going to move the shorter one. Oh, no. Okay, I'm going to move the longer one. The shorter one moves everything. And if I were to add those head to tail, remember the resultant that I am looking for is from the end of the first one to the tip of the last one. It appears it's probably going to end up in that second quadrant, right? All right, so let's add these together. What I'm going to do to figure out where that's going to be is I'm going to add these horizontal segments together. In order to find the resultants, you could still add them head to tail. Head to tail, if I were to add them, what do I notice? It's going to be a little bit negative. If I come over here and add them together, what do I get? Negative. Wait, what? I should know that was 7.4. Because I was the other way around. There we go. So it's just a little bit, and it's not very far there in my drawing. This right here is not very far into the X, negative X region. So if I look at the Y components, I want to add those together to get my resultant. So if I were to add those together, oh man, so it picks up the other one. There we go. If we add those together head to tail, it's going to go up quite a ways, right? So if I add those together, what am I going to end up with over there? 6.73. Okay. But they're not, oh, question up to that point. But they're not happy with that. They say, I don't want to know what it is in rectangular format. I want to know what it is in polar format. So now what do we have to do? Put it back into polar format. Don't worry, you don't have to write 4 different polar formats for this one, only one. Okay. If I were to put that into polar format, what do you need to do? It's going to go a little bit this direction. I'm going to over exaggerate. And then it's going to go up here. So how do you find this is 0.74? This is 6.73. So what do you have to do to find that piece? Pythagorean theorem. So I'm going to do the square root of 6.73 squared plus 0.74 squared. Okay, Jane, I'm going to leave that up to you. $6.77? Oh no. All right, let me grab my calculator.
Oh, I know it.
Second function square root 6.73 squared plus, I get 6.77. Oh, okay. All right, now I got to find an angle measure. How do I find this angle measure right here, this reference angle? That's the inverse tangent. So the tangent of my angle is equal to opposite over adjacent. So you want to type that in as the inverse tangent of 6.73 over 0.74. That's a nice 7. There we go. So if I type that in, (83.73). This is the reference angle, is 83.73. So how do I find the positive angle? Subtract it. So you take 180 minus 83.73, and it's going to be an angle measure of 96.27 degrees, which is only 6 degrees. So if I come back up here to where my actual resultant was when I drew my figure, this is only like a 6-degree angle right there. Not within your triangle itself, but just a little angle right there from the y-axis. Things you've done before. You've gone from polar into rectangular. That's the first step right here. And then to add them together, you just add the x components together, add the y components together, or I and j, whichever you prefer to have it stated. And from there, you go from rectangular back into polar. So my next question is, I better pause, or I better save this. How many of you know the law of cosines? Okay. I'm going to stop this.